We've been talking about how chemical dynamics can naturally lead to cycling behavior and chaos, and here we want to make that a little bit more explicit. A classic model that's been used to look at these types of phenomena is known as the Bruselator, and it's described by this abstract set of chemical reactions listed here in the middle of the screen. Now, these chemical reactions can be converted into a set of two differential equations, assuming that we hold the concentrations of A and B constant in the system. And in this case, we've added these different reaction rates K1 and K2, which describe the reaction rates associated with the arrows above. This system can be easily non-dimensionalized to a slightly simpler system, where we've combined parameters into effective parameters, little a, little b, and so forth. This system has a simple steady state at x equals a, this effective parameter, and y equals b over a ratio of effective parameters. Furthermore, what's very interesting about this system is that we're interested not only in what the steady state is, but in the dynamics leading to that steady state and whether the steady state is stable. Using techniques known as stability analysis, which is an entire field, it's possible to show that this steady state will be unstable for b greater than a squared plus 1. So let's take a look at what that looks like. If b is safely smaller than a squared plus 1, then you can start off at some initial concentrations for x and y, and these two chemical species will have some transient behavior that eventually leads to these two steady states that we described in the previous slides. Now, if we make b just smaller than a squared plus 1, so we make it very close to a squared plus 1, we see that you go to the same steady states, but now in the transient behavior, we pick up these oscillations that over time ring down, and it takes us a long time to go to the actual steady state itself. And if we make b just greater than a squared plus 1, so this is the case where things should be unstable, we now see that we have oscillations that go on forever. So this system naturally goes through an oscillation, naturally returns to specific states periodically, and in this case, how fast that's occurring, how frequently these states are passed through, that rate is increasing in time. Now, another way that we can look at these steady states in the set of dynamics is in a phase diagram of x against y. So this is looking at the paired values of these two concentrations, x and y. So time isn't explicit except in an animation, and in this first case where b is much less or significantly less than a squared plus 1, then we'll see that the dynamics have this simple case where you start off from any point in this space and you simply go to this one steady state. There's a little bit of transient behavior, but we go to a single fixed point in this system. This case where b is just less than a squared plus 1, where we had this ring down behavior to a steady state and oscillations in the transient, will look something like this in the phase plot. So you can see that we spiral in to the steady state that we expect to find. And so there's some very interesting oscillatory transient dynamics. And if we go above a squared plus 1, where we expect the system to be unstable, then we get this limit cycle. So we are constantly going to pass through this set of paired x and y values periodically with an increasing rate. What's interesting about these dynamics is that they're fully deterministic. So we haven't put any stochasticity in the system. We have this completely deterministic way of getting oscillations in time. And so it says that just the inherent dynamics of chemical dynamics, even without noise, can lead to really interesting oscillatory behavior. And that oscillatory behavior can be even more complicated than what we've been describing. So a classic system for looking at chaos is the Lorenz system. And so now we have a coupled value, or we have a triplet of values of x, y, and z concentrations, each related to these differential equations that I'm showing here in non-dimensional form. This was originally discovered in atmospheric dynamics by Lorenz, and can be mapped onto a variety of systems, including certain chemical dynamics. Now, what's interesting about this case is that This system gives rise also to fixed steady states, so where x, y, and z will go to a single value. But for other parameter values in the system, we'll find that you go to chaotic dynamics. And here's what those chaotic dynamics look like. So we're only looking at x, y, so there's a set of z values associated with all of these, and we're just looking at the projection into the xy space. In doing that, we see that you have this very complicated oscillation, where you not only oscillate over a complicated set of values in x and y, but you also transition between these two basins of attraction.